One of the neat things about R, although it can be scary the first time you encounter it, is that you can write your own functions. You do not have to depend on the functions that show up in the base installation or in the various packages. So functions typically will look something like this. You'll name the function. Now here, I'm calling it my.function, but it could be anything really. And then you'll have to tell R that you are building a function. You will pass a number of arguments, parameters. There could be 1, there could be 10 of them if you wanted to. There could also be no parameters. That's a possibility. And then you'll open a curly bracket and you will have a set of steps that actually tell you what the function does. And once that's done, you close the function with a curly bracket again. I'm going to give you a few pretty simple examples, and you'll see that they follow the same pattern. We'll write a function that actually multiplies two numbers together. And you'll say, why do we need to do this? There's already a function that multiplies numbers together. It's the product. Why? For instance, if I want to multiply 3 and 8 together, I just type in 3 times 8 and I will get, well, 24. It follows the same pattern. I'm naming the function. Here I'm calling it my.product. It is a function and it's going to take on two parameters, x and y. And what it does is it will multiply x and y together. So let's give it a go. We're going to try to multiply 3 and 8, which is what we had done before. So I'm going to run this. Here there's an error. It can't find the function. That's a bit odd because, I mean, function is right here. I've literally written it down here. I've written it down in the editor, but I have not compiled it to the actual workspace. So in order to be able to use the function, it needs to be compiled first. So now I have compiled it. We see the lines have been accepted by R, and if I try to multiply 3 and 8, now it knows what to do. It's equal to 24. We can also try a few other products. I'm going to write it slightly differently here. Because the function takes on parameters x and y, you can specify which of your numbers is meant to be x and which of the numbers is meant to be y. Let's see what happens. We should still be getting 24 here, right? And sure enough, that's what we're getting. Now the order matters only if you don't specify what each of the inputs is supposed to be, which argument it's supposed to be. If I switch it around, if I decide that my first argument will be my y and my second argument will be my x, well, I'm going to run this and I should still get 24. Right here, the order is not crucial because I have told R what's supposed to play the role of x and what is supposed to play the role of y. One last thing we can verify. The product is commutative, right? Whether you multiply x by y or y by x, you'll get the same value. Sure enough. Now, I want you to understand though, in that last product that we've run, the value of x isn't 3 anymore. The value of x is 8. Right? So if we do not specify what the variables are, what the parameters are, what the arguments are, it reverts to the order in which they are given in the function definition. Now let's take a quick look at a new function. We're going to call it myQuotient. As before, you remember that we actually have to compile the function if we want R to have access to it. I will do so by highlighting the block and running it. You might have noticed here every once in a while we have a string of characters which is preceded by a pound sign, a number sign, a hashtag sign. Well, this is a comment in R. Whatever follows the number sign on the line that it is given is not going to be compiled. It's just their document what the line of code is supposed to be doing. So if you look at it here, this hasn't really run here. No output comes out of this. The part that matters in order for us to be able to use the myQuotient function is to run these 3 lines. Let's say we try to divide 3 by 8. What's going to happen? I'm going to get 0.375. And that's true, that's the decimal representation of 3/8. In order for this to make sense, you need to be familiar with what this symbol is for division in R, just as you were familiar with what the symbol for multiplication. For easy, regular operations, that sort of more or less follows what you've been doing any calculator since we're a wee kid. But for some of the more complex things you might ask R to do, that's not going to be as clear-cut. So you have to get a good understanding, you have to achieve a good understanding of what the functions are for a lot of simple operations. And you can find a lot of that information online. I will add a link to a cheat sheet that you can use if you're trying to get familiar with R. We can play the same sort of game here, right? If we can specify that it is x, which is 3, and y, which is 8. Sure enough, get the same value. I can flip it around, and we'll get, again, the same value. Now I'm going to write it one last time, but this time I am not going to specify what my x is and what my y is, and I will reverse or flip the order in which they appear. And here we're going to get a different answer, a different output. 8 divided by 3 is not the same as 3 divided by 8 because division is not commutative. One thing you might have noticed as we were running the code, compiling it, now in your global environment you have functions. You have objects of type functions that are available to you in R, right? And if you want to keep them available for future sessions, you need to make sure you save your workspace at the end of the session. When we talk about the tidyverse in a future video, I'm going to show you ways in which you can pass arguments to functions, pass objects to functions in a very intuitive manner. For now, that's all we'll say about writing functions. Let's spend a bit of time exploring data with R, because in a sense, that's one of the strengths of R, our ability to analyze data, but also to explore data with the same tool. So we're going to start this working with a built-in data set called Swiss, the Swiss data set. Just run it so we can see that it actually does exist. Sure enough, this is something that is available in R as one of the pre-built data sets. There's a help file here and you can read it. It tells you information about various socioeconomic indicators for the French-speaking provinces of Switzerland around 1880. So we might want to see what this looks like in general. We know that we have an easy way to explore a data set by running the head function. Right? It's going to look at the first 6 observations and give us a quick idea as to the format of the data. So we get a number of provinces here: Courtelary, Delemont, Franche-Montagne, Moutier, Neuville, Porrentruy, and then 6 variables: fertility, agriculture, examination, education, Catholic, and infant mortality. And if we want to know what these things stand for or what they represent, we can find that information in the help file. Like for instance, examination would be the percentage of draftees that received the highest mark on Army examination. In this help file, we see that there's actually 47 observations, not just 6. If you run the head function on the dataset, you only see the first 6. So it's hard to get a sense of what the true structure is if you don't have the help file, but sometimes there's no help file to give you that information. You can get a sense of what the structure of the dataset is by calling the function str. You have to be careful. In many other languages, str stands for string, but this is not the case in R. str stands for structure. Alright, so I'm getting a bit of a strange output. The output is telling me that Swiss is a data frame, that is a type of object which is specific to R. It has 47 observations of 6 variables. This is good. It has 6 variables, as I've said, 4 of which are numerics, Two of those are integers, and here you see the values, at least the start of the list of values for each variable. That gives you a pretty good idea of what's out there. Let's see if we can do a little bit more. Perhaps we're only interested in displaying a specific column. Like say we're interested in the education column. Well, what would that be in the 1, 2, 3, 4th education? Well, I'm going to run the Swiss $education command. It is going to extract a column, a variable called education from the Swiss data frame. Here I'm seeing the actual 47 values in the Swiss education column. This can only be done if the object here, Swiss, is a data frame. If the object in question is not a data frame, then it doesn't have named columns, and then you cannot extract that specific column. There's other ways in which you could write that. You could also write it as, so this bit of code here is telling you from the Swiss object, you will extract, and here the square brackets are important, all the rows. By not specifying which rows I want, I'm displaying all the rows, and I want you to get the column which has been named education. Now I know what column this is. It's the 4th column, 1, 2, 3, 4. So I could also call Swiss square bracket, comma 4 square bracket, or if you feel more comfortable, you could write it like this. This would give you all of the observations. See, there's a blank space there. We're not specifying which observations we want in the 4th column. If you know what the name of the variable is, this is a neat way to go about getting it. Same with this formulation, because at some point you might have changed the order in which the columns appear and you might have forgotten you've done so. Working with the 4th column can be useful if your columns never change, but working with the education variable is easier, because if it gets somehow shifted to the end of the data set, you're still going to be able to get it without having to count the number of columns. You can also display specific entries, and this is going to be getting the entry in the data set which is in the 1st row and in the 1st column. And sure enough, I get the 1st row, 1st column entry, which is 80.2, the fertility measure for the province of Courtelary. So calling Swiss 1, comma will give me the 1st row, all of the observations in the 1st row. Calling Swiss, comma 2 will give me the 2nd column. So the 1st dimension, the square brackets, is the row, 2nd dimension is the column. I might be interested in only getting the 2nd and 4th rows, or eventually the 2nd and 4th column. I do so using the combining operator. This chunk is going to be looking at only the 2nd and 4th row in every column that we have available. Conversely, I might be looking at the 2nd and 4th column. Well, I want every row, which is given by not specifying the rows, and only the 2nd and 4th column in the combining operator. You can also specify that you do not want a specific row or a specific column, and this is done by using a minus sign in front of a series of columns or rows that you don't want. So Swiss, square bracket, no specification on the row, and -2 for the column will give me every column except the 2nd column. Scroll back up a bit, we're going to see, oh, I've lost the agriculture column. It's not lost in the data set itself, it's lost in the display. Right? If I go back and type in Swiss, run that, I'm getting, well, it's still there. I haven't erased it. Here's agriculture. Here are some other things you can do with data frame. Well, I can extract the column names into a vector. Let me run this here, and I'm seeing here a vector of character type with 6 entries. You can do this for the rows as well. Data frames are arrays or matrices for which the rows and the columns have been named. So there is such a thing as row names. And here we get a vector which consists of the 47 French-speaking provinces of Switzerland in 1888. I've shown you how to get a structure description of the data set using the str function. Let me just rerun it again so we see the output. There's a built-in function called summary, which can give us a little bit more information. Summary of the Swiss data set. that gives me what we call a 6-point summary of each variable. So it's going to look at each variable separately, and it's going to give me the minimum value, the first quartile, the median value, the mean, the third quartile, and the maximum value. And it does so for every single variable in the data frame. You can place that into an object. Let me call it test. So now I have a test table. A table is something like a data frame. It's not quite one. In theory, that means I should be able to extract an entry from it. Let's see what the entry in the second row and third column for this table are. Well, I get it's a string called first quartile 12. So second row would be the first quartile row. Third column is the examination column. Alright, so the summary statistics are easy to obtain, but they're not very complete. Like, we don't get a lot of information. You can get more information about the variables by using a function called describe, which is a function in the psych library. See what happens if you try to run describe without first loading the psych library. You will get, I don't know what this function is. So you specifically need to load the psych library, and then you can run describe. And here I'm getting more information about each of the variables. So these are univariate summaries. We're getting information about each variable independently of what happens with the other variable. As I've said, all of these are univariate measurements. Let's see if we can get some information about the interaction between variables. I can compute the correlation matrix. That tells me how much of a correlation there is between each of the variables. You get some correlation between, say, fertility and agriculture, a weakish correlation. Examination, on the other hand, seems to be strongly anti-correlated with fertility. So does education. But fertility is strongly correlated with the percentage of Catholics. And so this gives you a little bit of information about how the variables interact with one another. It's not a complete picture, but it's more than just univariate. We have some bivariate information. In other videos, we'll see how we can visualize multivariate connections, but for now, I just want you to see that you can obtain that information from some of the basic functionality. Well, this is a data set where every variable was numerical. We're going to take a quick look at a data set where some of the variables are categorical. So we'll go back to the insect sprays data set. We know it's a built-in data set. As a reminder, let's see what the head of this data set is. The type of spray and the number of insects that remained after the spray was applied. So I can run the summary here. I only have two variables. That shouldn't be too complicated. So what I'm seeing is if my variable is numerical, like the count, it does give me a 6-point summary. If the variable is categorical, like the type of spray, it's a factor, then it's just going to give me the count of how many observations in each category. I can look at the structure of this data set again. Not many surprises. Data frame is 72 observations of 2 variables. Here's a bunch of counts. Now look at the spray. Spray was a categorical variable. Categorical variables in R are called factors. Factors have levels, different values that they can take, A, B, C, D, and so forth. Except R doesn't really code them as letters, A, B, C, D, E, F. It actually codes them as numbers. So the level A is coded as 1, the level B is coded as 2, and so forth. And that can create some difficulties down the road. If I'm asking you to compute the mean of the insect spray's variable count, I just run the mean here, and I should be able to get something. Let's see what happens. I get a value of 9.5. But I could probably do this for the spray variable as well. Now, I shouldn't get an answer for that, right? The mean of A, B, C, D, E, F, that is not a well-defined question. We've already loaded the psych library, so I don't need to load it again, but then I can run the describe function on the insect sprays, and I get a bit more information. Notice here, because my variable is categorical, a little star next to it, and even though it's computing a mean, and it's computing a mean here by using the values associated to levels. Don't be fooled by this. Even though I have numbers, these numbers don't really mean it. It means nothing to say that the mean of various sprays is 3.5 if the sprays were A, B, C, D, E, and F. Even though R might, in some instances, provide you with a numerical value, it is not a numerical value. If you try to compute the mean of the insect spray, you'll get NA because you're working with factors. So in some instances, it knows to view the variable as a factor. In other instances, it doesn't. And if you try to get the correlation matrix for an object that has categorical variables, it will balk. It would say, no, can't do that. I can only compute correlations if all of my variables are numerical. You can do a little bit more with this. I would advise you to take a look at the example in the note. I'm going to end this video with a short word about NAs. NAs are specific values. If you're uploading data from a CSV file, for instance, and you had a missing value in one of the entries, puts a placeholder of NA. On its own, that's not problematic, but NAs don't behave the way that you think they should in this instance. So I'm going to do here a little example where we're going to build a data set called test, and what we're going to do is we're going to sample from the values 1, 2, 3, 4, and NA. Let me run just this little bit of code here that I have. I'm getting a vector with 5 entries, 1, 2, 3, 4, NA. So I'm sampling from that vector 1, 2, 3, 4, NA 100 times with replacement. Now, when you run this locally, you might get a different result than I do, because sampling is a stochastic procedure, it's a random procedure, but my version looks like this. Your version would look slightly different. So you see that every one of these entries is picked from 1, 2, 3, 4, and NA, and there's 100 of them in total. Let me do a quick summary here so we have an idea of what's happening. When I do my summary and there are NAs, they don't show up as being part of the minimum, the first quartile, median, mean, third quartile, maximum. They're separate. So 24 of my observations were NAs, and among the remaining 76 observations, the minimum was 1, the maximum was 4, we know that. And I have first quartile, median, and third quartile. I can do a little bit more if I just want to reconfirm that this makes sense. I'm not interested in full summary, just the mean value. And run the mean here. The mean is NA. So how did it get this value of 2.395 in the summary if when I compute the mean I get an NA? Well, you can actually ask mean to first remove the NAs from the test object. In the absence of this command, it's going to treat NA as basically a black hole. And NA plus a true value is NA. And NA times a true value is NA. So when you compute the mean, which is basically to add up all the values and to divide by the number of observations you had, at some point along the way you have to do the sum of all of these values and then eventually divide by 100. This is what the mean would be. But you get an NA because you could have 1 billion observations that are not NAs, and one NA, and the mean, the sum, everything would be NA as well. So a bunch of the functions that are of interest to you have specific functionality that allow you to remove any NA value. That's not always the best thing to do from a data analysis perspective. You need to understand why a value is missing. And when that's the case, typically you will come up with a mechanism to impute the missing value, to replace it by a good candidate for what the value should be. But that's not something you do willy-nilly. There's a lot of theory behind computing missing value. You can run the median, you can run the min, you can run the max, you can run all of the quantiles, and you will be recovering the information you had from this. Please take the time, take a look at the notebook where more examples are provided and more concepts are discussed.